So my name is Mikael Ronström. I have a background in MySQL for 15 years, and before that I developed an in-memory database called NDB cluster inside of MySQL that became MySQL NDB cluster. And now we forked that and working on a version called RonDB. So I'm going to talk about RonDB, which is a distributed in-memory database powering real-time AI. I will talk about its capabilities as an in-memory database. I will also talk about its telecom heritage, where always-on design, and even some hybrid capabilities nowadays that we can also do complex queries. So going back to the roots, why would you build an in-memory database instead of a disk database? So we did a major requirements collection in the 1990s when we started designing NDB. It was in the telecom space, so it has an Ericsson heritage, the world's biggest developer of telecom switches and things like that. And one of the most important requirements was latency. So latency had to be in the order of a few milliseconds. So, and in those few milliseconds, you had to do something like 10 to 30 operations. And it was a combination of reads and writes. So it was not just reads, it was also updates. You can think of, for example, if you have a mobile phone and you're walking around, then you have to update your location every now and then. So, and you update your services, you do all sorts of things. You see here the uptime requirements is 99.9999. That means actually less than 30 seconds of downtime per year. So that's a requirement that you have on a system that's used by mobile phones. And you can think about what would happen if a database goes down and you don't have the ability to make phone calls or use your iPhone. I mean, that would be a disaster. So it would be major news. So the major reason why we selected an in-memory database was that disks was simply too slow to involve in the whole thing. Another thing is that even if you do use disks, you still have a problem that the disk is just sort of, there is some caching going on. So latency is something you get very controlled if you use a in-memory database. Throughput was another problem that we needed to support, and that also is a major factor in choosing an in-memory database. So I'm going to present today is how we did use in-memory and how that benefited our architecture and our performance and made it more useful in the telecom space. Now, RonDB is actually used as a feature store in the real-time AI space. So in here, we are mostly doing reads. So it's the inferencing part of an AI. So you have trained your programs and you're now going to do inferencing. Inferencing here could be, for example, personalized recommendation systems. So it could be Spotify, or it could be something similar where you have your history of what you have been doing. And so every time you have to search in Spotify for something, Spotify knows your preferences and will use some queries towards RonDB to figure out how those things happens. Spotify was just an example. It's not necessarily a customer of ours, but it's a good example. And here you could have key lookups up to 100 million key lookups per second. So it's very, very high demands. So that's sort of is the latency requirements here is on the telecom side, you have to do 10-30 operations within 10 milliseconds, even with the load of 90% of the system load. And in the real-time AI space, you have to do bit batch key lookups where you look for 100 to 200 rows and get the response back in 1 to 2 milliseconds, even when you're doing 100 million lookups per second. So these type of requirements is the ones that was the base for the development. Now the architecture is a distributed system. So we have a layer called the RonDB API, and we put that on top of a normal transport layer using sockets. Could also use shared memory in some cases. On top of that RonDB API, we have a MySQL server, so it's integrated in MySQL. You can also integrate it in something we call RDRS, so it's basically a REST API server where you can do specialized things like batch key lookups, batch writes. But we also have a sort of a special RonSQL variant that does some more advanced SQL stuff that is faster doing it in RonSQL compared to doing it in MySQL. So that's the architecture. And now moving on to the internals and why is it good in an in-memory database. So the first thing is the hash index. So every table has a hash index. And actually we use 3 levels of hashing. The first level of hashing is to find out which fragment. And fragment is just a part of a table, and that fragment points you to which nodes in the cluster the data resides in. The next level is a linear hashing, where you find the memory page where you have your hashing elements. And the third level is to find your way into the page. So that means that you, with 3-level hashing, you actually get to the very cache, to the very sort of memory where your hashing elements resides. So that means that you get 1 cache miss when you're looking up in the hash index, no more than that normally. Linear hashing means that it's incremental expansion. It grows and shrinks naturally, no pauses for rehashing or anything like that. And the hash itself has an element header, and it's basically 2 32-bit words per element per row. And then there is a bit of overhead. So roughly 15 bytes of overhead per row is what you get. And what this means is that you have a lookup that is basically direct. There is no, if you have trillions of rows, it doesn't take more time. So it basically is constant time. And there's no caching, no reorganization pauses or anything like that. Now, the tuple storage is divided into 3 parts. There's a fixed part in memory, cache aligned, very fast. So usually the primary key resides in that area. You have a variable space part where you're space efficient. You have variable characters, you have blob parts, and you even have dynamic columns. And then there's a disk part. The disk part is the same as the variable size part, but it's on disk instead. So it uses a page cache as a normal disk-based database. So that just gives you the capability to have disk columns instead of in-memory columns. But for this presentation, obviously the in-memory part is the most interesting. So in order to get the best performance, we use a prefetch strategy. So after DBA's the hash index lookup, we prefetch all the cache lines of the fixed part, and that gives us a 5% improvement in throughput. Okay, we also need an ordered index in a database as usual. And instead of using a B tree as would be normal in a disk-based database, we use the T tree. A T tree is a balanced binary tree with multiple keys per node. So it means that it has fewer nodes than a B tree, less pointer overhead. So essentially the overhead of each row in this case is about 10 bytes, because we don't store the actual content in the tree. We only store pointers in the tree. So that means that the tree is very, very light in memory usage. And the use cases for the index is obviously order by mostly and inequality predicates. And so normally when you define a primary key, for example, you get both the hash index and the T tree ordered index. Okay, So in an in-memory database, it's still very important to do recovery. So we do the recovery through a local checkpoint, and we also have online backup. The local checkpoint is done with partial checkpoints. So that means that each checkpoint doesn't checkpoint the entire database. It only checkpoints the parts that have changed and a small part addition to that. So that means that even if you have a database size of several terabytes, you will still be able to sort of to do checkpoints every few seconds or so. And then you have a restore block that replaces the local checkpoint when you restart. You have a redo log that takes care of the redo to keep it up to the latest updates. And the backup is online, it's consistent while the system is fully operational. In order to do the processing, we also have a local query handler, and that basically is just the controller that controls accesses to the index, to the data, and to the ordered indexes. But it also contains the redo log. So not much, it's not sort of super important, but it's obviously an important part of the architecture. And durability comes from both the local checkpoint and something called the global checkpoint. So the global checkpoint is essentially where we create consistency points that we can recover. And whereas the local checkpoints is mostly to make sure that we can quickly restore all the data. So all of this happens in sort of in memory, but we store obviously the checkpoints and the global checkpoints. We also store that on disk so that if you have a crash, you can always come back. And when you come back, you start with the local checkpoints, you apply the redo log until the last global checkpoint, and then you have something which is consistent. And after that, you can also communicate with other nodes that are alive and make sure that you synchronize yourself so that when you actually come up again, you are synchronized with the other nodes. And there is also a transaction coordinator, obviously, so that you need, so it's a distributed system, so we use transactions. And we have a two-phase commit protocol, which has a takeover protocol. So a normal two-phase commit protocol would be blocking, but in our case, we are non-blocking because at the node failure, we start a takeover protocol. So we immediately have one of the surviving nodes take over all the transactions. And one important thing I mentioned already before is that it has telecom requirements. So that means that we have to sort of support very high demands on sort of uptime. So that means that at a failure, it has to be very, very fast in failing over to the other nodes. So most of the time, we figure out the failure based on that the socket closes because the operating system closes the process. So that takes about 1 to 2 milliseconds to detect. Then it has to be a distributed transaction that basically broadcasts the node failure to all the other nodes, and they have to decide which nodes actually survived. After that, you start the transaction takeover, and within a few hundred milliseconds, you're completely done. Everything is fine. So new transactions can start almost immediately after the failure. Those transactions that were in process when the failure happened will take a few hundred milliseconds, and then they are concluded as well. So that's how we get the sort of the high availability in the system. So one important thing, and this is maybe the sort of the most central parts, the most innovative parts of RonDB, that's the actual execution model. So we have a mutex-free signaling architecture. So signaling is the same as sending messages. Comes from the hardware world, the name signal. So a signal in the hardware world is a message. So it's asynchronous, so it means that you fire away and then it's up to the receiver to handle it. The queues that we're sending them in are lock-free, so there is no mutexes or any locks involved in sending messages internally, even though we're sending between threads. We're also using an old traditional way of doing things where we run to completion. So when you start executing a signal, you run it until you're done. It never blocks. There's no context switches happening when you're sort of changing between different threads. So that means that it's an asynchronous system, so you can essentially run thousands of queries at the same time. But they're executing one at a time in every thread. But the context switch between the threads is down to nanoseconds, since it's basically just switched to another message. So it's very, very fast to sort of handle many transactions simultaneously. And in order to improve the performance on communication, we collect messages from many different places and send them as a bigger package, because the bigger packages we send, the cheaper the communication is. So there are no deadlocks, no priority inversion, no unpredictable latency involved. And you can see here that you have a receiver thread that receives the data, the message. You have a transaction coordinator that takes care of the next step. You go to the LDM where you have the actual data and the hash index, the ordered index, and so forth. And then you send the response back. So there are 4 threads involved. And that actually means that we have a functional separation. And one of the key insights is that in order to get best performance, you need to keep the instruction cache very hot. And what we get here is we have 4 different threads. The receive threads, it has a lot of operating system code involved. The DBTC threads have a lot of sort of transaction-oriented code to execute, but it's completely different from the operating system. And then we have the LDM threads where we have the actual hash, the tuples, the scans, all of the data handling stuff. And that's usually the bottleneck. And it's very important to make sure that the LDM threads are not, there are no other code executed other than the LDM thread code itself. That makes LDM threads very, very nimble. And then we have the send threads that sort of collect things and sends them off to other places. In order to sort of, this whole thing means that often the receive threads and the TC threads, they sometimes have CPU available, but they have nothing to do. So because the LDM threads is the bottleneck. So in order to handle that, we have implemented something called adaptive read scheduling. So that means that any receive thread and TC thread can actually execute read-only operations on the data in the LDM thread. So they basically, the receiver threads and the TC threads, they can help the LDM threads with reading. So that gives us some free extra read capacity without having to add new LDM threads. So at low load, LDM threads handles all operations. At high load, they get assistance. And the adaptive read scheduling is kind of an interesting philosophical thing, because the CPU statistics is updated every 50 milliseconds or so, but that's a very long time in a computer. So in order to get more refined responses, we have queue sizes that we check also every 400 microseconds. So basically, if the behavior changes within a millisecond, we will react to it. We also have adaptive CPU spinning. So that means that a thread that doesn't have anything to do, instead of going to sleep, which takes a long time, and it takes a long time to be woken up, you have to wake up the operating system if you go to sleep. So we actually measure the effectiveness of spinning instead. So basically we just spin, wait for the next message to arrive. And we do that by keeping statistics about how long time we expect to be sleeping before we wake up. And if the sleep time is fairly short, then we decide that let's spin instead of go to sleep. So we only go to sleep when we think that it actually saves power and so forth. So, and obviously when we spin, we do it in an efficient way. So the second thing, scalability, fragment versus thread. So obviously if we always do key lookups, we want to use as many CPUs as possible so we can have many fragments. However, scans, they tend to prefer to have as few fragments as possible. So those are conflicting goals. So the adaptive read solution also means that we can actually have fewer fragments and still scale to more CPUs. So those the adaptive read scheduling has another goal. It also wants to decrease the number of fragments that we have. So this gives us better performance in sort of scanning the data and not just key lookups. Okay, so we have, as already mentioned, we have several interfaces. You can have a MySQL server, you can have a REST API server, you can use the RonDB API directly, and you can even use a Redis interface, which we call RonDis. And the interesting thing with RonDis is that you can insert data using a Redis API, and then you can use MySQL to read it. So that's a kind of cool feature. The REST server is very much geared towards our feature store. So we have a feature store REST API. We have a RonSQL query engine used for push-down aggregations and things like that. So there is lots of ways you can use RonDB. And we also work heavily on sort of pushing down the sort of complex query execution into the data node so that we can have parallel query execution. So in this particular case, we have a push-down join aggregation where we have a three-way join, and we are calculating the count and the sums. So we can have here it's a sort of combination of key lookup and transactional and analytical things in the same engine. And obviously the focus is on the sort of being an online inferencing engine. The reason why we're doing this is because in the feature store, let's do this first, we have something called shift right. So that means that you might want to calculate your aggregations online, on demand, instead of doing it in the background. If you do it in the background, you can do it in a different system, and then you just do a key lookup when you do the inferencing, online inferencing in the real-time AI. But with shift right, immediately when you insert the data, the inferencing engine can see the data and can do the online aggregation. So that means that in an AI system with inferencing, you actually want to use both key lookups, but you also want to do complex queries that aggregate data from multiple rows. So that's one feature that's very important as well. And finally, we have online management. So if you want to have a database that's online all the time, then you obviously have to do all sorts of management operations. So you can change the software as an online operation. You do a rolling restart of the data nodes. There's no downtime. You can add drop indexes. Those are built in the background, and there is no downtime because of that. You can add columns. That's basically you add a dynamic column, and it's always nullable. So that's an online operation again, no downtime. You can change the number of replicas. You can start with a single replica or 2 replicas, and then go to 3 replicas, and then decide, no, I want only 2 replicas. And so you can go back and forth on the number of replicas, and there's no downtime in adding or removing replicas. You can change the storage. You can even scale the system to more data nodes and rebalance the data, and that's also an online operation. So anything that you want to do, you can do it almost as a rolling restart with 0 downtime. So that's a very important feature, both for real-time AI as well as for the telco space. And in order to sort of to handle all this, it's mostly about when you do the push down aggregation and when you do filterings and all sorts of things, you can actually use an interpreter inside RonDB. So that means that where filters could be pushed to the actual row, you can have atomic operations like A equals A plus 1 done in the data nodes instead of having to go back and forth between the database and the API. You can do group by, sum, count. You can do filters in the join predicates. You can even do binary searches. We have a community user that runs a graph database on top of RonDB, and they use binary search in the binary data, and they use the interpreter for that. So you can do an interpreter is very useful in order to push down calculations to the left of the system. And finally, if you compare to other databases, we have a shared nothing database. It's RonDB, and it's synchronous replication. Failover times is less than a second. It supports full SQL. It even supports parts of Redis, although that's still experimental. It supports hybrid transactional analytical support. It has a REST API, and it can do online DDL. So for example, Redis, yeah, it's a good key lookup thing, but there's no analytical queries. You have DynamoDB. It's again a key lookup without sort of very advanced functionality on the query side, and it also is quite expensive. Whereas RonDB is actually open source, and you can use it all together with us or on your own. And so as already seen on the slides, RonDB is powering Hopsworks, which is the company that I work for, and where RonDB is basically the platform for everything. And there is also global replication. I forgot to mention about that, but that's essentially the presentation. There's also other things like, for example, adaptive send runtime configurations. There is a CLI. There is Kubernetes deployments, of course, and lots of other things that I haven't mentioned, but time is too short for that. So thank you very much.